Hey, this is Mr. Bainey, and we're going to take a look at, hey, what's up, Math 1? We're going to take, hello, this is Mr. Bainey. Let's take a look at lesson 16.4, Reasoning and Proof. And in this lesson, we're going to start looking at how do we go about proving a statement. And we could prove things like theorems or even conjectures that we make. And so we're going to look at what exactly those are. So in this first page, you'll see that we have some vocab words. These aren't going to be that important that you remember these, but you may come across these words, especially conjecture. A conjecture is kind of like when we make a hypothesis in science, something that we think is going to be true, and that we can use some sort of reasoning. So here you see two different types of reasoning that we can use to prove that our conjecture is true. And sometimes it's not true. And in that case, we'll look at how we can prove it's not true. We're not going to go through this part here, but down below, you'll see our next vocab word, theorem, is a type of statement that we can actually prove. And so one of the theorems that you may have seen last year is called the Pythagorean theorem that involves triangles. And because it's called a theorem, we can actually prove that it's true. Right, on the second page, 816 is a vocab word, counterexample. So instead of answering this discussion question here, I'm going to actually give an example of a statement that we can provide a counterexample for. So I'm going to be coming up with the statement here. If a number is odd, then it is prime. So this is our statement, and even this could even be our conjecture, right? So we know that numbers that are odd, such as 3, 5, 7, and so on, that those are actually prime, and they're actually odd numbers. So some may think that this is a true statement. And if you go just a little bit further, even to that next number, we're actually going to show that this is false, that the statement that I wrote in blue is false. And that's where we provide a counterexample. A counterexample is coming up with something with specifically an example where we want an odd number, but we want to show that it's not prime. Okay, so we want to actually make the first part true and the second part false. And this type of statement, it's actually called a conditional statement, or some of you may know it as an if-then statement, used a lot in geometry in making statements. And you'll see them in a lot of postulates and theorems, even in some definitions. So counterexample, one of them you can come up with is the number 9. And actually, I didn't talk about what prime meant. Prime is a type of number that only has two factors, 1 and itself. So the number 1 is not prime just because it only has one factor, just 1. 2 is prime because its factors are 2 and 1. So I'm going to actually add that to our list here. So 2. 3 is prime because its factors are 1 and 3. 5 is prime because its factors are 1 and 5, and so on. The number 4 or the number 6 or even the number 9, right? The number 9 is not prime because it has 3 different factors. It has 1 and 3 in itself. So that's what makes it not prime. You could provide more counterexamples, although just coming up with 1 is enough to say that, hey, this statement isn't true. But something like 21 would work, or something like 35 or 81. There's a bunch of them in this case. In some cases, for some statements, there will only be one possible counterexample, and you'll see that in your assignment. For this statement, there's a bunch of them. Okay, the statement that I put in blue there, the one that we proved was false, again, I talked about that being a conditional statement. Here's the definition. So a conditional statement can be written as if-then. The first part we call the hypothesis, kind of like our conjecture, right? Or like a hypothesis in science. and then the second part is called the conclusion. So if the hypothesis is true, the conclusion must be true for the conditional statement to be true. Okay, so you're going to see a lot of conditional statements here. Some of these should look familiar. So we have a lot of properties, and the first four are ones that we've used quite often, even though we don't really state it. We use those to solve equations. All right, so when we add something to both sides of the equation, we are using the addition property of equality. When we subtract 5 on both sides of an equation, we're using the subtraction property of equality, and so on. So we use the first four a lot. Reflexive properties, symmetric, and transitive properties. These might seem a little obvious, but they're necessary for us to start writing proofs. So reflexive, I'm just going to write some examples off to the side, just so you can see how they're being used. So if we say like the number 7 equals 7, right? That's reflexive property. Symmetric is something like if we say 2 equals x, right? When we solve an equation, that means that x equals 2. Okay, we just switch them around. So symmetric says that we can do that. A transitive is, I'm going to write it down here at the bottom because this one's a little bit longer. If we say something like x equals 5 and 5 equals y, well, we can combine those two statements together and conclude that x is the same as y. It's equal to y. Okay, and that's using the transitive property. Substitution is something that we've used quite a bit. So if a equals b, or if like a equals 9, right, then 9 can be substituted in for that a. So again, we've used this quite a bit. On the next page, we're going to just take a look at the bottom here, number 6, and think about what properties are being used in each of these statements. So the first one we have, if x equals 2, then 2x equals 4. Well, how do we get from our if phrase to our then, right? From our hypothesis to our conclusion. So let me spell this out a little bit more for you. How do we get from x equals 2 to that part? Well, we multiply 2 on both sides. And that means this is the multiplication property of equality. I'm going to abbreviate this. So multiplication property of equality. I'll just leave it like that. If you want to pause it to try these other ones before I do them, go right ahead. But I'm going to keep moving along here. 5 equals 3a. Therefore, 3a equals 5. So here's my if part. My then is leading to there. So it looks, you have to observe what's going on from the first part to the second. And it looks like they're just switching. So that means that's the symmetric property. And for the third one, if t equals 4, then 5t plus 7 equals 27. So we start with the t equals 4. We know that that's true. How do we get to this part? Specifically, how do we know it equals 27? Well, if we do 5 times 4, right, I'm substituting the 4 in for t, and I add 7, that's actually equal to 27. That means we're using the substitution property of equality. So I'm just going to call it substitution. And the very last part, if 9 equals 4x and 4x equals m, that means that 9 is equal to m, right? How are we getting from those two statements to the final statement here, 9 equals m? Well, since we had to combine the two statements together, that means this is the transitive property. Okay. So get used to trying to see these properties in proofs or examples of proofs, or when you're solving equations, things like that. On page 818, is another definition for us. Linear pair. So linear pair has two parts to it, and you'll see up at the top here, this is a definition of what a linear pair is. And then in this box is the theorem that involves the linear pair. So you have to try to distinguish those two apart. I'll try to help you out with that. So the first thing that we need to know is that a pair of supplementary angles equals 180 degrees. Supplementary means if two angles are supplementary, they add up to 180. One other angle relationship, it's not mentioned here, but there's also complementary angles that adds up to 90 degrees, something that it's good to know, and possibly even a good idea to put on your index cards for your notes. Okay, back to linear pair. So definition of a linear pair. Let's write that down over here to the side. Oops. So linear pair, I'm going to try to actually use explain it more simply than the way it's stating it there at the top. So the first part is it does say it needs to be adjacent. Adjacent means that it shares a side and vertex. Side and I'll mention what it looks like in the picture. Okay, so shares side and vertex. And the second part is that it makes straight line, makes a straight line. And if you recall, a straight line or a straight angle measures 180 degrees, and that's where the supplementary part kicks in, right? So it makes that straight line, and the way that it describes it here in the definition is kind of confusing. It says whose non-common sides are opposite rays. Opposite rays means a line. Okay, so let me identify those parts here for you. So here we have angle 4 and angle 3. These both are adjacent to each other because here's the vertex right here, and there's the side that they share, right? So this side is a part of angle 4 and a part of angle 3. So that's adjacent, good. And then it makes a straight line. So these are the non-common sides. Here's for 4 and here's for 3, and that creates a straight line. So that's a linear pair. Again, that's the definition. Now let's talk about the theorem. The theorem says if we have a linear pair, right? So using our definition, is this a linear pair? Yes, it is. Looks like it. Adjacent, makes a straight line. Then the conclusion is they're supplementary. Remember what supplementary means. It means that the two angles add to 180 degrees. Okay, and it states it down here as well. You'll also have to use stuff that we learned in 16.1 and 16.2, and that's the segment addition postulate and angle addition postulate. It mentions it here for you. Okay, so go back to 16.1 and 16.2 to review those if you need to. Here at the bottom of page 819, let's try out this example. I definitely recommend you look at the previous examples on this page and the page before as well. But we have two angles, LMN and NMP. They form a linear pair, right? So that's important. Remember, you have to think about your definition of a linear pair and then also that linear pair theorem. The measure of LMN, I'm actually going to write this part down. Angle LMN is twice the measure of angle NMP. So notice, as I was reading it, I was kind of writing out our statement here. So if I know the measure of this one, or specifically if I know the measure of this second one right here, I just multiply it by 2 to get this one. So I'm actually going to rewrite this, but instead of writing all of these letters, I'm just going to use X, right? The measure of angle NMP is my variable. So let's draw this. Well, if you look at the names of these two angles, what's the vertex? The vertex is M. So I know it's going to be a linear pair, so here's my line. And right here is my M. Okay. There's my shared side. Sorry, it's not a straight line. And then if I look at the letter that they share the letter N. So N has to go there. All right. The bigger angle is LMN because it's twice the measure of the other one. So I'm going to put L here. And then on the other side is going to be P. So I know that the measure of angle NMP is X. I replaced it with X degrees. Remember that over here. This is X. And then the other one is 2X because it's twice what the other one is. Now that I've written expressions for both of them, I can set up my equation. So here's my equation. The big angle plus the other angle, right? Because they are a linear pair, they add up to 180 degrees. And we just solved this. 2x plus x is 3x, and then that equals 180. Divide by 3, so x is 60. So that means this is 60 degrees, and that makes this one 120 degrees, because you just do 2 times 60 to figure that out. Okay, and that's it for number 8. On page 820, please review these postulates. I'm just going to talk very, very briefly about them. The first one, oh, by the way, you saw your first postulate on lesson 16.1, the second postulate on 16.2. So here's the third, fourth, fifth, sixth, seventh postulates in geometry. So our first one is through any 2 points. You got a point here and a point here. There's only one line. We can't draw other different lines through those same 2 points. Right, through any 3 non-collinear points, you need to know what non-collinear means. There is exactly one plane that contains all 3 of them. That means I can't draw another plane, another surface that contains all 3 of these non-collinear points. If 2 points lie in a plane, then the line containing those points is also in the plane. So if the points are in this plane, the line is also on the same plane. Okay, that's important. This is postulate 6, I believe. If 2 lines intersect, here's one line, here's the second line, they intersect in exactly 1 point. That means they're not going to intersect a second time or a third time or anything like that. And the very last postulate is if 2 planes intersect, you have this plane going up and down, you have this plane kind of going forwards and backwards, so like a 3D figure here. They intersect at a line right here. And remember, because the planes go on forever in all directions, the line goes on forever as well. Okay, let's try to use, look at those postulates, or try to apply those postulates to this picture that we see here. And as I was looking at this in class, I mentioned this to some of you that this is difficult for me to actually understand the 3D-ness of it. You see these dashed lines? The dashed lines show up in a picture whenever something is behind another figure, which means this part right here is behind this part of the plane. You want to think of this part of the plane as something that's coming towards you, and this one went behind the other plane. So this plane that kind of looks like a rectangle is going left and right. That's how I'm seeing it. Okay. This part of the plane, this is kind of coming forwards and backwards. So this one is behind and this one is in front. All right. Now that feel free to pause it and try to wrap your head around how this is supposed to look, because it's challenging when you're putting a 3D figure on a flat surface like a piece of paper, right? Or you're watching this on a video. So you're watching it on a 2D surface, but it's a 3D figure. Anyways, here we have descriptions, and we want to name or identify what it's describing. So the first one is the line of intersection of two planes. So they intersect at this line here. I'm going to put it in red. So this line is where the two planes actually cross each other. And so we can call that line M. That M, that's like a cursive M at the very, very top. We can call it FG with a line notation above it. So we call that line FG. We can call it line GJ. And we can always switch those around, right? We can call it GF or JG, or we can use JF or FJ. There's a lot of names for this one. As long as we pick any 2 points on the line, we can name it. If you want to pause it to try the other ones, go right ahead. I'm going to keep going here. The second one, point of intersection of two lines. Well, we only have 2 lines in this whole picture, this whole figure. So point J is where the 2 lines will cross. All right, so this one has a very specific answer. Coplanar points. So coplanar means that the points are on the same plane. From the looks of this figure, it looks like all of these points are on the same plane. So we just need to pick 3 of them. So I'm just going to say points. It's probably looking for, coplanar means it's probably looking for 3 non-collinear points. So we're going to throw H in there. I don't know why I put a comma at the beginning. Point H, and then I'm going to pick 2 of the other points. So we could say G and F. Right? If I picked J and F, that's also fine. So when we talk about being on the same plane, 3 points on the same plane, we also want them to be non-collinear. So I'm going to make a note of that here. And the very last one is 3 collinear points. Collinear means on the same plane, since non-collinear means, sorry, on the same line. Non-collinear means not on the same line. So the ones on the same line are the points F, J, and G. I'm going to actually take a look at one of your assignment problems just to kind of get you started here. On page 823, number 5, we're going to give a counterexample for each conclusion. So if x is a prime number, that means this is our hypothesis, remember. Then x plus 1 is not a prime number. So we want a prime number where if we add 1 to it, it's not a prime number. Okay, so we want a number that is a prime number, but when we add 1 to it, that is a prime number, right? We want to show that this is false. If we can make this true and then this becomes false, that's a counterexample, right? So our example here, I'll just kind of give you the answer. There's only one counterexample we can come up with. If x equals 2, well, that means x plus 1 would be 3. Yeah, we just add 1 to it. Well, x equals 2, 2 is prime. And if we add 1 to it, we get 3. That is also prime. So that's our counterexample. All right, so try to be specific when you're giving your counterexample. Don't just say x equals 2 or the number is 2 and leave it at that, right? Try to kind of follow through to the conclusion and show that this is not matching up with our conclusion here. Okay, that's going to do it for this lesson. Thanks for sticking with me here and hope this was helpful to you. Have a good day.